Thank you.
I feel like they're any kind of Greek it's really very, very small. No, if they're just yell at them.
All right, so the first one, if I'm going to say f, g, and h are first degree polynomials. Then the curve given by this vector valued function r of t equals f of t I hat plus g of t j hat plus h of t k hat is a line. Yeah.
Should we write this down?
It's up to you. I mean, it's not a bad thing to refer back to. All right, so so first degree polynomial, what are we talking about? X or something like x 2x plus 3, right? So let's think of an example. For example, we could say that f equals at, g equals bt, and h equals ct. We could add a constant on there, but those are nice linear polynomials. So from the vector valued function, this says that x equals at, y equals bt, and z equals ct. Is that a set of parametric equations for a line? Yeah.
That is.
So this is true. So a line as a vector valued function is going to be a vector valued function with linear components. All right, let's go the other way now. If we'll think about the converse. If the curve given by x equals f of t, y equals g of t, and z equals h of t is a line, then f, g, and h are first degree polynomials.
Contrapositive is false.
It's false.
Bruh.
No,
It's false.
the contrapositive is you switch the order and put not in front of everything.
Yeah, Dylan.
Curve.
If the curve
Dylan.
is not given anyway. All right, so if this curve is a line, then all of those coefficients, all of our components are first degree polynomials.
False.
False. What would
X squared, X squared, and X squared.
Yeah, false. Give me the.
If they're all the same.
if they're all the same? So we could say r of t equals t squared I hat plus t squared j hat plus t squared k hat, for example, as a counterexample. This is, if we relate the components, x equals y equals z. That's symmetric equations for a line. So this curve would be a line. So if we have any function any vector valued function where we have the same function for each coefficient, we're going to get a line. So that would be false. One of my students that took the class that did not do See You Succeed that went to CU said he wished he had, because all of the exams at CU, they had questions like, is this true, sometimes, always, never? And he hated those kinds of questions.
I was just going sometimes. Every time.
Next one. Two objects. Traveling along these curves. R of t equals ti hat plus t squared j hat. And what is this curve? Parabola, right? Y equals x squared. And I'm going to say u of t, not the same curve. 2 plus t. Will collide. Well, what?
We're learning. Dylan.
They're just traveling along these curves. What? Well, once we figure out if it's true, then we have to figure that out.
Well, it could intersect in twice.
What dimension?
Well, what has to be true?
The I hats and the J hats.
The I hats and the J hats have to be the same, right? So we would need the components to be the same at some particular time. So we need t equal to 2 plus t. And what does this tell us?
That's no good.
And 0 equals 2.
0 is equal to 2.
That's no good.
So this would be false. They do not collide. This line does not intersect that.
What about if you said t squared equals
Well, so for them to collide, the x component and the y component have to be the same.
Oh, okay.
All right. Let's see. This one is a nice one. R of t, this is related to that last example we did last time. Plus t cosine t k hat. So the question is, this curve lies on the paraboloid. Paraboloid x equals y squared plus z squared. So the curve that we talked about in our last example last time, the curve was on a cylinder. This is asking, is this curve described by this vector value function on this paraboloid? So what do we need to do? Yeah, let's should we see if this is true?
Sure.
What's y squared?
Yes, it's true.
Y squared is t squared sine squared t. And z squared is t squared cosine squared t. Y squared plus z squared equals what? T squared, which is x is t squared. Is that this paraboloid? Yeah. Well, that's true. So what would this curve? So thinking about what the curve that helix that we sketched last time, what would this curve look like? it would be like a helix, right? Because this is giving us an motion in the x along the x-axis, because the paraboloid lies along the x-axis, and it's spiraling. We get kind of a circular motion. But what does this t on the circular motion do? It gets bigger and bigger.
And then it gets small again.
So we end up with, let's draw a quick sketch. So here's our paraboloid, x equals y squared plus z squared. So we get a paraboloid along about the x-axis, like that. And then our curve is going to go like this along that paraboloid, but it's going to get bigger and bigger and bigger, like so. And it should, if I were sketching it a little more accurately, the coils would get further and further apart as well, because we have this quadratic we have the t squared. So it would be more and more stretched out as it went further from the origin.
Whenever we see things that have the sine squared plus cosine squared in some dimension, that means it's a helix that's wrapped around some
Something.
other
Mhm.
shape.
Yeah.
So that could be a cylinder or a paraboloid or any
Right,
other figure.
right.
Okay.
Uh-huh. So I don't know if it's a technical term, this kind of a parabolic helix. I think that would be a good term for it. All right. Let's talk about representing a graph with a vector valued function.
That's two ways down.
Kyle, don't take any shit from him.
Hey.
What am I in right now?
He's dead.
What am I in right now?
You're in a sad.
So it's going to be necessary, we're going to need to, in the future, translate from a specific graph to a vector valued function. And we'll do this in several different contexts. We'll start with one that hopefully is a little bit familiar, because we did a similar thing when we talked about parametric equations. So I want to start with do an example here. We want to find vector valued functions for the boundaries of, and here's, we'll do just a plane region for this first one, then we'll do a little more complicated one. So here's my region, or here's my curve.
Is that like a sector of a circle?
And this is the origin. This is at 10. This is x squared plus y squared equals 100. This angle is 45 degrees. So we want to find vector valued functions for the boundaries of this region. So just looking at that, are we going to be able to do this just with one vector valued function? Do we think? No.
We're
Two.
gonna need 3 because we need
So
two vectors.
so we're looking at this, and I forgot to put an orientation. So we want to go around. We want our vector valued function to go around the curve this way. So we did this with parametric equations, where we came up with parametric equations for particular curves. So let's call this one 1, 2, and 3. And we're going to say for boundary 1. Well, what's y on this boundary? Y equals 0. That's a nice, easy one. And what do we want to do for x? X equals t, and t is going to go from 0 less than or equal to t less than or equal to 10. So we could say for r1 of t is ti hat Just leave it at that. 0 less than or equal to t less than or equal to 10. And there's a vector valued function for that boundary. How about for the second one?
Cosine or 10 cosine.
Yeah, let's do this in polar coordinates since this is a circle. So x equals
10
and I would recommend since we want x to start at 0 when t equals 0. Let's use sine for x. You could use cosine, that would work as well. You could just use a different parameter. I'm just going to start t, my parameter, at 0. So x is 10 sine t. Y is going to be 10 cosine t. And t is going to vary from
0 to
pi over 4. So r sub 2 of t is 10 sine t I hat plus 10 cosine t j hat, and we have 0 less than t less than or equal to pi over 4. So that's our second boundary. That was not too bad. For the third boundary, well, one, we need this point. Yeah, well, can we just plug in pi over 4 here? Yeah? So what do we end up with? And before we even do that, what is this line? This line is y equals x, right? Yeah. So what does this point come out to be? 5 square root 2, 5 square root 2?
Keep it up, Dylan.
All right, so we know that y equals x. And we want x and y both to go from 5 square root 2 to 0. So how are we going to parameterize that?
Y x equals t, y equals t.
From 0 to 5.
5 root 2 to 0.
5 root 2 to 0? Okay.
But you can't go up.
0 to 5.
No, so we want the vector, we're given this orientation.
Oh, okay.
So we want to go from 5 square root 2, 5 square root 2 to 0, 0.
So 5 root 2 minus x.
So how about do 5 square root 2 minus t? Y equals 5 square root 2 minus t. And 0 less than or equal to t less than or equal to 5 square root 2. Right? That would work. It wouldn't be incorrect to say,
5 root 2 to 0.
yeah, we could go x equals t and y equals t, and we could go from, t goes from 5 square root 2 to 0.
Shouldn't that just be from 0 to 150? Because you have the 5 root 2 for the coefficient.
Well, so when t is 1 here, we'd get, did you say from 0 to 1?
Yeah, which should be negative 1 to 0 actually. So they're both positive.
So since we're subtracting, when t is 0, x is 5 square root 2, y is 5 square root 2, right? So we'd be here. And then when t is 5 square root 2, 5 square root 2, we'd be at 0. So we'd start here
Oh, that's
and go to
subtracting. I thought
right.
that was.
Oh, you thought I'd added? Yeah, if I'd added, then I needed to do what you said. And we have, for this particular parameterization of that curve, we'd have 0 less than or equal to t less than or equal to 5 square root 2. You could parameterize it in different ways. This seems like a nice way. This definitely a nice way for the circle. All right, questions there? All right, let's do a three-dimensional example now. All right, we want to sketch the curve of intersection of x squared plus y squared equals 4 and z equals x squared. So we want to sketch that curve, and then we want to represent it with a vector valued function. And this problem is nice. It gives you the parameter. X equals 2 sine t. Now, sometimes the problem will give you the parameter, a parameter that they want you to use for the parameterization, but this, the fact that one of the curves is this, one of the surfaces is this, suggests how we're going to want to parameterize that. All right, so let's sketch this. X squared plus y squared equals 4. What is that? Circle with radius 2, and we're in 3 dimensions, so z can be anything. So what is that? It's a cylinder. There's that cylinder, a portion of that cylinder. How about z equals x squared? It's a parabola, but we're in 3 dimensions. So it's, y can be anything. It's a cylinder, yes, but the shape is parabolic. So we get a parabolic cylinder along the y-axis. So I'm going to sketch part of it here so we can get the curve. So there's that portion. And what we're thinking of is this. This is going to continue along here. And this cylinder is going to intersect that other, the parabolic cylinder is going to intersect the circular cylinder. So the way that I visualize this, that I thought I'd think about it, is I think about this, if this solid thing were a knife and it's slicing through this thing. So the first place it's going to touch is down here. It's going to intersect here, if we had a little piece of it, as we're pushing it along. And then we're going to get this kind of parabolic shape here as it cuts through the side there. And we're going to get the same thing along the other side. As it cuts through that cylinder. So the first year that I taught this class, I didn't have Mathematica, so I made a model. So you can pass this around. Here's my model made with paper towel tubes. So the circular cylinder, the parabolic cylinder, and the curve of intersection is going to be there.
Oh, is that like little?
Kind of little sort of. You can pass it around.
Okay, we're good now.
It's a visual model in the 3rd dimension.
And then I also have, since I got Mathematica, I did a Mathematica. So there's a cylinder, and there's the circular cylinder, the parabolic cylinder cutting through it. The curve is the blue curve there. So there's our curve. I like this. And then on the next page, so there's the 2 surfaces with the curve highlighted. When I first did it, I didn't know how to highlight the curve. I was really proud of myself when I figured out how to highlight the curve on there. And then the second one is just the curve. There's the curve.
So it's that little sine wave thing.
Right, so here's the parabola
Okay, we're good.
cutting through. If I turn it this way, I get the circle. It's my axes are not symmetrical, so that would be the circle. And then that would be looking at it from, where are we? Okay, that would be looking at it from this side. There we go. So it's kind of a Pringle shape, but a little more, but it's not the surface, it's just the curve. Just the outline. Yeah, that's someone ate just the middle of the Pringle and left just the outside.
Nope, 0 width.
Right.
Perimeter.
All right. All right, questions? Oh, now we need to represent this vector valued function with the parameter. Represent it as a vector valued function. Well, this part should be pretty easy. If x is 2 sine t, based on this, what does y need to be? Y needs to be 2 cosine t. That'll get the x squared plus y squared equals 4. And z equals x squared? Sine squared t. So r of t is 2 sine t I hat plus 2 cosine t j hat plus 4 sine squared t k hat. So there's a nice representation of a pretty complex curve. And if we go back to this Mathematica, there's what I plotted, 2 sine t, 2 cosine, that's the x component, the y component, and the z component, from 0 to 6.3, which is 2 pi. T went from 0 to 2 pi. Yeah. So that's one of the benefits of 1, parametric equations, and 2, vector valued functions. We can represent pretty complicated curves pretty nicely. And what we're going to talk about, so next time we'll start doing some calculus. Oh, I need to talk about limits and continuity. We'll start doing some calculus with these things, and we'll talk about if we think of a physical object moving along those curves, we'll talk about velocity and acceleration. All right. Questions? Yes.
Just kind of a question that was related to this. Why don't we use component form for this? Why do we write it with the I hat, J hat?
We can use component form, and you'll often see it in component form. I don't know.
Is it acceptable?
Yeah, absolutely. To use it's perfectly acceptable to write this like this.
Yeah.
Right.
So that's what we think is more logical.
And I think you'll see it. You'll see them, and I try to use both. I realize I've been doing one.
Well, I think that was one.
Yeah, no, and this is perfectly acceptable. All right. Limits and continuity.
Oh, I thought we were at homework.
Not quite.
I mean, you started right in the age, so.
I almost forgot to talk about limits and continuity.
How much space is this?
Very little.
Okay, very little.
This very little space.
Like 4 lines.
Pretty much, yes. So, limits and continuity. Because of what we know about vectors, and because of what we know about limits, how we apply limits to functions, what we do with limits and continuity is apply what we already know, component by component. So we find the limit of each component. We decide if each component is continuous. So the limit as t approaches something is a limit for the x component. The same limit for the y component, the same limit for the z component. You just do the limits component by component. For continuity, same thing, you determine continuity component by component, but I want us to remember the definition of continuity, and we'll write it in terms of a vector valued function. So we're going to say R of t is continuous at t equals a if. So let's remember what we need for continuity. What has to be true for continuity?
It has to be differentiable.
No, that's the other way around. Differentiability implies continuity. All right. If I start, I think if I start writing something, we'll remember. R of a exists. The limit. What is it? So the limit has to exist, and then the limit has to. So the limit as t approaches a of R of t has to exist, and the limit as t approaches a of R of t has to equal R of a, the function value at the point we're interested in. That's our definition of continuity. Our function has to exist, the limit has to exist, and the limit has to equal the function value.
Is there any way for the function to exist, or the limit to exist, but not the function to exist?
Yes.
Mm-hmm.
Yeah.
Something like that.
Or just one of those things where it's like the piecewise functions. It's like
Piecewise, yeah,
subject to this function.
Right,
and
right,
something else.
exactly. All right, so that's all we need to know about limits and continuity. Apply it component by component. Okay.
Are you trying to
Yeah?
Gonna go to the Japanese suicide force and kill the dead body? No.
Okay. But he's making Jake callers. Like, he lives in such a cool house. He does such cool things. Yeah, but everybody hates him. I want to be like him, except everyone will love me. So not like.
When you make it big, remember us.